That's because we'll ask you to upload the video to YouTube, Ariana.
Okay, okay.
Cool.
All right. Okay, let me make some of this stuff go away. All right. So, today I am going to be talking about the GNS representation theorem. And this is covered in the C-star algebra notes from pages 39 to 44. So, the main goal for today is we want to prove this theorem, the Gelfand-Naimark theorem, which says that every C-star algebra A admits a faithful, non-degenerate representation, pi, um, from the C-star algebra A to B of H. And it also says that if A is separable, then pi can be chosen to be separable. So, first, let's just remind ourselves about what a representation is. So, um, maybe I'll make it a little bit bigger. A representation of a C-star algebra A is a pair pi h, where h is a Hilbert space and pi from A to B of H is a star homomorphism. Um, oh, also, I meant to say, uh, please stop me at any time, ask me a question. I might not see the chat. So if you see someone else put something in the chat and I didn't see it, please just let me know. Okay. But, um, all right. So, I say a star homomorphism. Technically, really, it's a C star homomorphism. But we can say just star homomorphism because star homomorphisms between C-star algebras are norm decreasing, therefore continuous. So every star homomorphism is going to be a C-star homomorphism. Um, okay. And an immediate corollary is that every C-star algebra A is isomorphic to a norm-closed star subalgebra of B of H for some Hilbert space H. This is really cool. It just kind of lets us see these kind of like abstract C-star algebra things as a much more like concrete thing. So, that is a nice corollary. Um, Throughout the talk, I will pretty much usually assume that A is unital. Um, did my screen stop sharing?
Yeah, I think I can't see the notes anymore.
Yes.
Yeah, I can't see them either. I wasn't sure if it was just me though.
Sorry about that, guys. No. How do I do this? You can tell I don't use any technology, hardly ever. Okay. All right. Okay, I'm not quite sure where it went off. So I'll just say one more time. An immediate corollary of this theorem 7.1 that we want to prove is that every C-star algebra um, is essentially a norm-closed star subalgebra of B of H. Throughout, it's in the notes and in my presentation, I'm generally going to assume that A is unital. I'll try to say otherwise. But you can see example, or maybe it's exercise 7.16 and remark 7.17 and the notes for why we can't always just like unitize. Um, but yes, so generally I'm gonna assume that my C-star algebra is unital. So let's see. So our first step towards proving theorem 7.1, um, first we want to look at this definition. We say that a linear map phi from A to B, where these are C-star algebras, is positive if for any positive element A, phi of A is a positive element in B. So, um, I use Laura's notes on on Overleaf, so if she recognizes this, that's where I got it. Um, recall, we know that the positive elements of A are all of the form A star A for any A and A, and B, the positive elements of B are all of the form B star B. So I was kind of hoping that if you want to participate, I might ask questions out loud. Feel free to participate or just type in the chat. Um, Also, if you don't want to, you don't have to. I'll tell you the answer. Okay. Essentially, we just want to say that phi is positive if and only if phi of A star A is of what form? Like, how do we want to be able to write? Like, for it to be positive, how can it be written? I don't know if I'm asking that question well. So maybe in this case, I'll just tell you what I mean. So phi is positive if and only if phi of A star A can be written as B star B for some B in B. Um, so some examples. If phi is a star homomorphism, it is automatically positive. Can you guys just quickly tell me why that is? So, Mhm. okay. So if we have phi of A star A, how can we write this? Yes, exactly. So we can write this as phi of A star, phi of A. Very good. Um, all right. And the next definition that we want to talk about is the definition of a state. So a state on a C-star algebra is a linear functional, which is positive and is of norm 1, where this is the norm. Um, if we take the set of all states on A, we can see that um, this is a subset of the unit circle of the dual space, and we call S of A the state space of A. All right, so for some examples of states, so if we have a C-star algebra A and a representation of A, we can fix a unit vector in H and define this map phi of A to be the inner product of pi of A applied to xi, inner product with xi. Um, and this is an exercise in the notes to check that this is indeed a state. Um, Another good example is if you have a character, it's both a state and a representation. Um, I realize that I just started using this. I might write this, I will probably write this for representation throughout the talk. All right. And proving this is also an exercise. Um, some other exercises. So from the notes, if you have a positive linear functional, then phi is automatically bounded. Okay, so here specifically, I'm just to be clear, I'm assuming that one is in A, that it has a unit. So in this case, phi is automatically bounded with the norm of phi being equal to phi evaluated at the unit. And phi is star preserving, i.e., we have this. Um, so in the case that A is not unital, We know, well, have y'all did approximate units, right? Have y'all done okay, yeah. So every C-star algebra admits an approximate unit. So if A doesn't have a unit, then we say that the norm of A is equal to the limit of absolute value of phi of E sub lambda, where E sub lambda is this approximate unit. Um, Another exercise that is good to do is to show that the state space is a weak star closed convex subset of the unit ball of the dual space. And so by Banach-Olaglue, we know that the state space is weak star compact, which is nice. Okay, so this this next exercise we're gonna talk about a little bit more, but let me just put it up here so we can look at it. So let's fix a positive linear functional phi from A to C. We can define this map from A cross A to C in this way. When we do that, we get that this map is a positive sesquilinear form on A and hence satisfies the Cauchy-Schwarz inequality. So first, I wanted to ask you guys, could you tell me what a sesquilinear form is? I don't know if y'all have talked about them yet. Do y'all know what a sesquilinear form is? I mean, and they're in the prerequisite notes. So,
I think we haven't talked about them in a lecture, but they are in the notes.
okay. So, a sesquilinear form is a map that is going to be linear in the first coordinate and gosh, now I can't think of the word conjugate linear in the second. So we'll check that for this map. So first, let's talk about positive. So we want to send positive elements of, oops. So to be positive, we want to send positive elements of A cross A to positive elements in C. But actually, this map, no matter what you put in, so, well, okay, so I guess really maybe I should have asked Laura. I don't really know what positive elements necessarily are in here. I guess like they're positive if like an element like A, B is positive if and only if A and B are positive.
Well, I think with this, when we have something going into the complex numbers,
Mhm.
a sesquil like positivity here
Mhm.
means that when we have the same element
Ah, okay.
plugged in.
Okay.
Yeah. So I think that the use of that, it's just a little bit different because now we're talking about like a multi or sesquilinear map.
Oh, okay. So
Yeah.
sorry, guys.
You're
Um,
great. You're doing
but
great.
Can I step in and say something?
yeah.
No.
So what this means is like if you feed in a positive element, which is something like A star A, then that's always a positive thing. I'm not sure.
But like if you were to like what does it mean for a sesquilinear form that takes Cartesian products as inputs? Because we're kind of just talking about like a positive or positive definite pre-inner product or
Mm.
yeah.
Do we mean it's positive semi-definite here?
Yes.
Yeah.
And we want it to be positive definite, which it's not necessarily yet. But yes, that's what I think the use of that word positive is referring more to,
Okay.
yeah.
Okay. So, all right. So that was my mistake. Okay. So,
You didn't make a mistake. You're doing great. Keep going.
all right. So if we take A and put it into both coordinates, we get phi of A star A, and we know that this is going to be positive for all A and A. So let me also just be clear right here. Um, so phi is positive, like semi-definite. All right. And to show that this is a sesquilinear form, um, so we just want to check that it's linear in the first coordinate. So this is going to be phi of lambda, let me put an extra parentheses, plus c. Sorry, I forgot my b star. Since after COVID ended, I told myself like I never want to use tablets again. And so I really struggle with using my tablet. So sorry, guys. But this is going to be phi of lambda b star A plus b star C. And then we know that here the lambda is going to come out, and we have phi of b star A plus phi of b star C. And when we rewrite it back in the like the bracket notation, this is going to be phi plus, oops, CB, so phi. So this is linear in the first coordinate. Let's check that it's conjugate linear here. So this is going to be equal to phi of lambda b plus c star A. We're going to distribute the star, so we get lambda bar b star plus c star A. C star A. And then again, we can, using the fact that it's linear, and then we can rewrite it like AB plus AC sub phi, like this. So we get that it's conjugate linear in the second. So yes, we've proved now that this is a positive semi-definite sesquilinear form. So we're gonna use this again later, but just really fast. We have this lemma 7.8, which I am going to skip the proof of. And it says, let A be a C star algebra. Oh, but I should say the proof is in the notes. So you guys can reference that. Let A be a C star algebra and phi be in the dual. Then phi is a state if and only if phi of the unit is 1. So I guess here I am assuming that 1 is an A. So yes, that is a nice result. Okay, so we talked about states. That's like the first part that we needed to learn about to be able to solve or to prove theorem 7.1. Step 2, we're going to talk about representations and this GNS construction. So first, I just want to recall that a representation pi is non-degenerate if pi of a h is dense in h. So that's just saying that pi of a oops, H, closure is H. All right, so here, theorem 7.9, this GNS construction, we're gonna let A be any C-star algebra. So here I'm not assuming unital, just any C-star algebra. If phi is a state on A, then there is a non-degenerate representation, pi sub phi, and a unit vector, psi sub phi, and H, such that for all A and A, phi of A is going to be equal to the inner product of pi of A applied to psi sub phi with psi sub phi. Um, this representation, pi sub phi and H sub phi, um, I guess I should have wrote H sub phi right here. We call this the GNS representation associated to phi, and psi sub phi is a cyclic vector for the representation. So the motivation for this proof is that we want to build H using A, like we want to build it out of A. So let us, so I'm just going to prove the unital case though. So I think it's an exercise to prove the non-unital case in the notes. So let's assume A is unital and consider it as a vector space. By exercise 7.7, I kept dropping the sub phis. Or maybe they had them, maybe, yeah, they had them. Okay, sorry guys. So we know that this is a positive definite sesquilinear form, semi-definite, definite sesquilinear form. If it was just positive definite, that is, whenever I plug A into both components and it's equal to 0, this is true if and only if A equals 0. This sesquilinear form would be an actual inner product on A. So how can we get around this? Does anyone know what to do whenever we have elements that we want to get rid of in a space that would make our space use it somehow to make a nice space? Exactly. We want to quotient out by those elements. So first, can you guys tell me so I'm gonna define n sub phi to be all those elements that I don't want. Um, and how do I define this n sub phi? Could you guys tell me in the chat? I mean, I kind of already said it's A and A such that I think it's technically phi of A star A equals 0. I think that's how we defined that. Yes. Oh my goodness. Or let's just say, yeah, okay, let's just say it like that. All right, so then n sub phi is a norm closed subspace of A. You should check this. And we can define an inner product on the quotient in this way. So it's almost exactly like what we had above with the sesquilinear form, but now our elements are like this. And it's not obvious necessarily that this is well defined, because of the way these elements are, right? We're on a quotient. So to see this is well defined, you need to show that n sub phi is actually equal to the set of all elements in A, the set of elements A, such that phi of B star A equals 0 for all B and A. Um, Again, I'm not going to show this, but you should do it. It's a good exercise. All right. So now, just looking at this, this is not a Hilbert space, but we can take its Hilbert space completion with respect to the norm induced by this new inner product that we defined. Um, and we can define now our representation. So we're going to define pi sub phi from A to B of H sub phi like this. So pi sub phi of A is applied to an element in the quotient, and we define it like this. Can you guys tell me why it's enough to just define this function on elements in the quotient? Do you guys know? So the reason why it's enough to define it on elements in the quotient is because the way we defined it, the quotient is dense in it. So every element in H sub phi can be written as a limit of these elements, or of the form like this. So that's why this is enough. So now, first we must check that this map we defined is actually a bounded linear operator. Um, so let's do that. Um, so first, we know that A star A is a positive element. And exercise 3.11 from the notes tells us that we have that A star A is less than or equal to the norm of A star A times the unit. Um, so for some x in A, we have this inequality. So first, A of x star A of x, we're just going to rewrite it like this. We're going to use this inequality to be able to replace this with this. And then this is just a constant, so we just pull it out. All right. So then if we apply phi to this element, we get this inequality, which ultimately says that this is going to be less than this. Okay. Now, again, we're trying to show that this is bounded, so we want to take the norm squared. So first, the norm of pi sub phi of A norm squared is going to be the supremum over all x in A, such that phi of x star x equals 1 of this inner product. All right. And can you guys tell me, well, okay. Anyways, so we get that this inner product is going to be equal to, this is just by definition, uh, of the inner product, phi of this element. All right, and then we know from this equality or inequality above rather, we get that this is less than or equal to the supremum of x over a of all of this. And then this is just equal to 1, so really we're just souping over a constant, so we just bring it down. And then we know from the C star identity that it's equal to norm of a squared. So taking square roots, you get that the norm, so taking square roots, you're going to get that pi sub phi of a is less than or equal to norm of a. So this is going to be bounded. Now, we want to check that this is a star homomorphism. Again, we're trying to show it's a representation. So since pi sub phi is unital, I say y. You guys should check y. It is non-degenerate. By exercise 4.26, it says that it gives this result. So now we have our representation, and then the last statement of this, let me go back to it. Where did it go? It says that there's also a unit vector such that phi of a is equal to the inner product of pi of a with that vector, inner product with that vector again. And sorry to be scrolling around, but this vector in this case is going to be the unit plus n sub phi. So you could check that. We can check it. So let's just go ahead and check it. So if we have pi sub a, or pi of a, excuse me, 1 plus n sub phi, 1 plus n sub phi. How is the left-hand side, or what is the first coordinate gonna reduce to? Could you guys tell me in the chat? How do we rewrite what's in the first coordinate? Very good. And then this is just gonna stay like this. And then just by definition, oh wait, hold on, sorry. Okay, so now can you guys tell me what this inner product is gonna be? How did we define this inner product? Sorry, I keep forgetting to write my fees. Maybe let me scroll back. Oh, well, let's just check this. So we said here, when we define it like this, we drop the pi sub phi and over here. So actually, right here, we don't want to include the pi sub phi of a. We just want to call this a. Okay, so now this inner product we define to be phi of, it would technically be 1 star a, which is just going to be phi of a. So that's how we get that. Is that okay, everyone? Feel free to let me know if you have any questions. All right, so there's that proof. Okay, so next, a few results that I will state but not prove. We're just gonna use them. Um, Lemma 7.12 says that for all A and A, such that A is non-zero and normal, there exists a state such that the absolute value of phi of A is equal to the norm of A. And a corollary of that says that if F is a weak star dense subset of the state space, then for any A in our C star algebra, we can write the norm of A as being the sup of the absolute value of phi of A, uh, suping over all of these phis in this finite, oh, sorry, not finite, weak star dense, finite later. Um, okay. So with all of this, we can now prove 7.1. So let's just remind ourselves of the theorem. So every C-star algebra admits a faithful non-degenerate representation, pi from A to B of H, and if A is separable, pi can be chosen to be separable. All right, so we're immediately going to start by using this corollary 7.13. So we're going to let F be a weak star dense subset of the state space, and we're going to define pi to be the direct sum of all of the pi sub phis that we're considering, where each pi sub phi is defined like how we did above in 7.9. Okay, so now we're going to fix A and A because pi is a star homomorphism. We know it's norm decreasing. Um, also, all right, so the norm of pi sub phi of A squared, um, this is just by definition. Um, and then we say that this is greater than or equal to pi of A evaluated at 1 plus n sub phi. Can you guys tell me why we have this inequality here? So this is just because this is souping over all of them, and then this is just one of them. So this soup is going to be bigger than just one. Am I right, Laura? Yeah. Okay. Um, now we I'm dropping my fees again. I'm so sorry. Okay. So now I'm just rewriting this using I mean, that's just by definition. Okay. And then again, we want to use the formula we had before that said when we do pi sub phi of A applied to 1 plus n sub phi, this is going to be, well, okay, let me put, well, that's a D. I really wanted to be. B plus n phi, we define this to be AB plus n phi here. So here it's more simple. We're just gonna technically have okay. Um okay, now I think I started writing weird things. Um okay. I do think I wrote weird things. So let's just cover that back up. That's not what I meant. Okay. So pi sub phi. Let me just delete this. Okay. Because I don't want to look at my mistakes. All right. So this inner product, so first we write this as A plus N sub phi, A plus N sub phi. And what is this inner product going to be? We define this to be phi of A star A. All right, so let me delete that. That was phi of A star A. All right, now the norm of the represent. So remember, we defined pi to be this phi and f, pi sub phi. So the norm of pi of A squared is equal to the sup over phi and f of all of these. But we know that from this inequality above, we know that this quantity is greater than or equal to this quantity. And we know by another result above that this sup is equal to the norm of A star A. I don't remember the number of the result, but it's above. Which by the C star identity is equal to norm of A squared. So if you take square roots, you get that pi of A is going to be greater than or equal to norm of A squared. And, not norm of A squared, just norm of A. But also above, we had that A was, sorry, I'm writing things in a way I shouldn't. Pi of A is less than or equal to the norm of A. So that means that they're actually equal. Therefore, pi is actually isometric. We originally, in the statement of the theorem, we said that we wanted pi to be faithful. Do you guys remember from the previous lectures why what the definition of faithful is and why being isometric gives us that it's faithful? Okay, I'll just go ahead. Uh, so it's faithful if it's injective, and isometric map is going to be injective. Uh, since pi sub phi is non-degenerate, for each phi and f, so is pi. Um, A nice fact is that if A is separable, S of A, the state space is 2, so you can take F to be countable, and the separability of A implies the separability of H sub phi for all phi, so H is separable. But I put a star here because there is something to check. The norm on A is not the same as the norm on phi of H. So something you should look at and play with for yourself is how do these norms relate? Why can we say that? Um, so that's something good to think about. Um, okay, I know just a few more minutes, and y'all didn't talk about group C star algebras yet, right? Like y'all
Correct.
didn't. Okay, okay, okay.
And also, Ariana, you actually have until 10 if you want. I didn't, or sorry, not 10. You have 14 minutes, not 4.
Oh, okay, okay, okay. Um, okay, well let's go here. Let's go here. And maybe I'll stop to ask questions. So, definition. Um, we want to define this new representation, pi of u, to be the direct sum of pi of phi, where phi is like we sum over every element of the state space. Um, and this representation is from A to B of, so okay, we call it, I write it here, but let me just write it here so it looks a little better. This Hilbert space is going to be the sum over phi in the state space of H sub phi. So this representation is from A to B of this Hilbert space. And we call this the universal representation of A. This is not faithful. There's a remark in the notes, and it's a little long, but I thought it was a good one, so I'll just kind of say it out loud. Um, for the If you wanted to get a faithful representation, you could take a weak star dense subset and sum over that instead. But however, we really want to take all the states and get pi sub u because the associated von Neumann algebra, pi sub u, pi sub u of A, the double commutant, is isometrically isomorphic to the double dual. And both are often called the enveloping von Neumann algebra of A. Is it enveloping or enveloping?
I think it's enveloping.
I think it's enveloping too, but okay. Just wanted to make sure. Um, all right. So, question. What does this main theorem that we proved say about abelian C-star algebras? So the Rees-Markov-Kakutani representation theorem says that states on C0 of X are in bijection with probability measures on X. So anytime you evaluate a state, or yeah, evaluate a state, you can really think about it as integrating F with respect to the corresponding probability measure to phi. So in this case, so this is what we're trying to make into a Hilbert space. We needed to mod out by those elements in n sub phi. And for C0 of x, those elements consist of the set of C0 functions on x, which are functions that are zero off of a mu sub phi null set. So we take the Hilbert space completion and we get that it's just isomorphic or isometrically isomorphic. Isometrically isomorphic to L2 of x mu sub phi. And pi sub phi on C of x represents or pi sub phi represents C sub 0 of x as multiplication operators. Sorry. And then you can see how the multiplication operator is defined here. Okay, so an exercise from the notes. What does the universal representation of an abelian C-star algebra look like? What's crazy is like I know I've seen this problem when I was a goalie, and then when I was a goals TA, I don't remember if we did this so I don't know if I've actually ever worked this problem out by myself. But I'm imagining it's a good problem and everyone should do it. Um, so yeah. The last exercise that I'll talk about is if you let A be a C-star algebra, show that for uh, all B and A, there exists a representation pi from A to B of H and a unit vector psi and H such that norm of pi of B applied to psi is just norm of B. And they give a hint that says apply lemma 7.12 to A equals B star B. And I think I'll stop there because everything else was kind of like referencing the group C-star algebras and stuff like that. So I'll stop here and answer questions if anyone has them. Thank you. And I should stop recording, right?